Hello students, let us study another topic that is about sulfur dioxide. So sulfur dioxide is SO2. So let's see the preparation. First one is sulfur dioxide form when sulfur bond in oxygen or air. So sulfur bond in oxygen or air, we will get sulfur dioxide. Then another method is laboratory preparation, lab preparation. That is any sulfite treatment with dilute acid, say sulfuric acid, we will get sulfur dioxide. Sulfite ions are SO3 2 minus, reacts with acid, that means H plus ions are there, we will get SO2 and H2. So this is a reaction. So sulfite is treated with dilute acid like sulfuric acid, we will get sulfur dioxide. This is a laboratory preparation. Then industrial method of preparation or large scale preparation. So that is from sulfide ore on heating with oxygen. So heating in oxygen. Here this process is actually called a roasting, which you have studied in metallurgy. That is, in the process of roasting we will get sulfur dioxide as the byproduct. Here we can use FeS2. So it's a sulfide ore of iron which is heated in presence of oxygen. So that process is called a roasting. So sulfide ore heating in presence of oxygen, that is a roasting. In this process we will get Fe2O3 and SO2 as the byproduct. So SO2 will be formed as the byproduct of roasting. So that is another method, so which is the industrial method of preparation. So these three methods are used for the preparation. So this is about preparation. Let's see the properties. First of all, let's see the physical properties. Physical properties are actually sulfur dioxide is a gas. Sulfur dioxide is a gas. It's a colorless pungent smelling gas. Colorless pungent smelling gas. Then another point is it is highly soluble. It is highly soluble in water. We know sulfur dioxide, when dissolved in water, we will get sulfurous acid, H2SO3. So this is called a sulfurous acid. So sulfur dioxide when dissolved in water produces sulfurous acid. This is just like carbon dioxide. Carbon dioxide dissolved in water produces carbonic acid. Just like carbon dioxide, sulfur dioxide dissolved in water produces sulfurous acid. So which is highly soluble in water. Now let's see the chemical properties. So in chemical properties, first of all we will see what happens when sulfur dioxide is passed through NaOH. Sulfur dioxide is passed through NaOH. So this is important question. Sulfur dioxide is passed through NaOH, what happens? So here we can write sulfur dioxide is passed through NaOH, SO2 plus NaOH. Here SO2, you know, it's an acidic oxide. It's an acidic oxide. Sulfur is a non-metal, so it's an acidic oxide. SO2 is an acidic oxide. So NaOH is a base. Here you can write the products very easily. That is, acid plus base is salt and water. Salt and water. Salt will be Na2SO3. Na2SO3 and H2O. So sodium sulfite, Na2SO3, sodium sulfite. So in the next step we have to check if excess sulfur dioxide is passed. If excess sulfur dioxide is passed, so we have these products Na2SO3 plus H2O. When excess SO2 is passed through this solution, we will get NaHSO3. So this is sodium bisulfite or sodium hydrogen sulfite. So this is actually again similar to carbon dioxide. In lime water test we have seen the similar reaction, where we have seen when carbon dioxide is passed through lime water, it turns milky. If excess carbon dioxide is passed, the milkiness disappears due to the formation of bicarbonate. So just like carbon dioxide, here sulfur dioxide reacts similar to that. That is, sulfur dioxide is passed through NaOH, we will get a salt. If excess sulfur dioxide is passed, we will get a bisulfite. So this is the reaction. So this is happening when sulfur dioxide is passed through NaOH. Then another two important reactions are sulfur dioxide and chlorine. So what about the reaction between sulfur dioxide and chlorine? So in this case, I have written here sulfur dioxide and chlorine, we will get SO2Cl2, that is called as sulfuryl chloride. Sulfuryl chloride is formed, and here the important point is charcoal is used as the catalyst. In another reaction, that is SO2 plus O2 form SO3. Here V2O5, that is a catalyst. Vanadium pentoxide, that is a catalyst used. In these two equations, you have to remember the name of the catalyst. So the name of the catalyst are important in these two cases. So this is actually an important step in the manufacture of sulfuric acid, which we will study later. So SO2 plus O2 gives SO3, that is the next reaction. So these two important reactions are to be studied. Here you have to remember the catalyst. So first one is charcoal, that is about sulfuryl chloride formation. Second one is vanadium pentoxide V2O5, that is about SO3 formation. Then another important point is moist sulfur dioxide. Moist sulfur dioxide, that is sulfur dioxide and water. So this is actually a good reducing agent. So it's a good reducing agent. That's an important point. So moist sulfur dioxide is acting as a good reducing agent, where we can see two reactions where Fe3 plus on reduction gives Fe2 plus. So 3 plus changes to 2 plus, that is reduction. It is actually reduction. So here this happens in presence of this reducing agent. So Fe3 plus SO2 plus H2, that is moist sulfur dioxide. So this actually acting as a reducing agent, and Fe3 plus reduces to Fe2 plus, and SO4 2 minus, that is here this changes to SO4 2 minus and H plus. So these are the products. So the main point is Fe3 plus changes to Fe2 plus. This is actually a reduction reaction. And SO2 plus H2O, here this acts as a reducing agent. This will definitely undergo oxidation. So that changes to SO4 2 minus and H plus. So this equation is not balanced. You have to balance this equation and consider it as a redox reaction and balance in that way. So this is the equation Fe3 plus, that is the reduction part. This is actually reduction. So this is actually oxidation. So oxidation and reduction takes place in the same reaction. So it's a redox reaction. You have to balance it as a redox reaction. So the main point is Fe3 plus changes to Fe2 plus, that is reduction. Here SO2 plus H2O, that is moist sulfur dioxide, acts as a reducing agent. This is one reaction. Then another reaction is MnO4. MnO4 is actually from KMnO4, you know, KMnO4, potassium permanganate, MnO4 minus. MnO4 minus changes to Mn2 plus. Here, MnO4, here it is 2 minus, so it will be 8. So plus 8 will be the oxidation state of Mn, and plus 8 changes to 2 plus. So it is also reduction. So this reduction reaction takes place in presence of SO2 and H2O. So moist sulfur dioxide will reduce this MnO4 2 minus or MnO4 minus to Mn2 plus. So we can write the equation MnO4 MnO4 minus plus SO2 plus H2O. This is the reducing agent, and this changes to the reduction takes place here, and Mn2 plus is formed, and again SO4 2 minus and H plus. So here actually this is the reduction part. Reduction takes place, and here it is oxidation. So oxidation and reduction takes place in the same reaction, so it's also a redox reaction. Here you have to balance this by considering it as a redox reaction. So this is the reaction where we can see MnO4 minus or KMnO4, that is purple color. So KMnO4 potassium permanganate is purple color, and if we pass sulfur dioxide through this, we will get Mn2 plus, that is actually colorless. So we can use this reaction as the detection of SO2. So how can you detect SO2 gas? So that's an important question. Here, when SO2 is passed through, KMnO4. KMnO4 is actually purple. It changes to colorless solution. It changes to colorless. So this is due to the presence of SO2. So SO2 can be detected by using this reaction. So this is purple. This is purple. This become colorless. So colorless due to the formation of Mn2 plus. So MnO4, that purple color is due to the presence of MnO4 minus. So when SO2 is passed through KMnO4, it changes to colorless. So this reaction can be used to test or detect the presence of SO2. Then another point is about the structure of SO2. So SO2 is similar to ozone. So we can draw the structure like ozone. So SO2 is angular in shape, angular or bent V. So structure of SO2. Two, four, six, eight. 2, 4, 6, 8. 2, 4, 6, 8. This is one structure, and another structure also can be drawn. So here single bond, here double bond. So this is the second structure. So it is actually the resonance hybrid. The real structure is the resonance hybrid of two canonical structures. So two resonating forms, two resonance structures are possible for SO2. So two resonance structures are possible. So we can say the SO bond lengths are identical. So in the case of O3 we have studied. So here also we can say the SO bond lengths are identical. SO bond lengths are identical. Why SO bond lengths are identical? Because SO2, the structure of SO2, or it is actually the resonance, it is actually the hybrid of two resonance structures. So resonance structures are possible for SO2. So The bond lengths are identical. Bond lengths are identical in the case of SO2 also. So two resonance structures are possible for SO2. So it's a resonance hybrid of two canonical structures. So the bond lengths are identical. It is actually angular in shape, angular or bent V. So bent V-shaped structure or angular in shape. So this is about sulfur dioxide.